Sir Arthur Conan Doyle once said, "A change of work is the best rest." So let's forget about LLMs, generative AI, code generation, completion, etc. for a while, and let's take a break with ultra high energy astrophysics. So for those attending and watching us via live stream or even watching the recording, in the comment of the thread in our Slack channel, I have left a link to this data lore notebook that, well, you could find it. I hope. I saw that some people have found it already, so you could open the copy. You could open my version of notebook and see me editing it, or you could create your own copy and try to play around with it throughout the whole workshop, and ask any questions if you will have some. So let's get started. So first, what are cosmic rays per se? So cosmic rays is a charged particles that are coming from outer space to our solar system. There are a lot of possible origins for such particles. It could be some reactions happening in the galactic core. It could be binary stars merging. It could be supernova explosions, black holes merging. A lot of ultra high energy events happening in space generate such particles, and some of them reach Earth. When they hit our atmosphere, they cause a cascade reaction called air shower. So we have there on the skin, we have a primary cosmic ray, like primary particle, a single particle hitting air, and when it hits air, cascade reaction happens. So the molecules of air falling apart. They emit like smaller particles that hit other molecules of air, and we, in the end, like on the surface of the Earth, we receive a cluster of these smaller particles. So we can detect the cosmic ray itself from the Earth, but we could take a look at these particles and try to find out what exactly happened up there. Why and how we study air showers? So first of all, the thing is, primary particles of cosmic rays could have 1 million times higher charge than those particles than we have in Large Hadron Collider. That means that if we are just like in software development, where our test fixtures should test fixtures should check for some edge cases, checking the data produced by these ultra high energy particles helps us to check edge cases for physical theories. So we could check if some particular physical model matches the data that we obtain from these events. So here's another example of the cosmic ray. Now it's from the Pierre Roger Observatory, which is an array of 1,000 detectors of different kinds. So when the array hits the atmosphere, these detectors detect all the secondary particles and trying to figure out what was the original cosmic ray, what was its energy, mass, direction, etc., etc. In this particular workshop, we'll be exploring the data produced by the Cascade. Cascade, or Karlsruhe Shower Core and Array Detector, was an experimental detector array in Karlsruhe, Germany, that operated for over 20 years, and it was accumulating. It accumulated over 300 millions of air shower records, including cosmic rays with energies up to 200 peta-electron volts, which is 30 times more than large LHC's max energy. So Cascade There's another photo in color with more details. This is basically a 16 by 16 grids of different kinds of detectors. So basically, muon detectors and electromagnetic detectors that check all these secondary particles and record the information of air showers. So, air shower is this cascade event caused by the cosmic ray. So what we are going to do throughout the workshop, we'll train a neural network that would predict the mass of the original charged particle that came and caused air shower based on the air shower data. So the fancy term for this stuff is called cosmic ray mass composition analysis. So this notebook, data lore notebook, already contains a baseline neural network, data pipeline, evaluation pipeline, and aside from everything, it contains some small code hints. Each one is marked with a to-do comment, and throughout the workshop, you could try to find these to-dos in code. They hint at the parts of the code that you could edit yourself and try to tweak the model or tweak the data pipeline and see how would it affect the result. Once you run the pipeline, you will get the confusion matrix, which is a graph showing the accuracy of predictions for each class, each particle. So we have protons, helium, carbon and oxygen matched in the single class, silicon, and ferrum. So throughout the workshop, we'll see why we need not just the accuracy, but the confusion matrix, because since we need to find mass composition, like the number of particles of each class, we need something more than accuracy, because accuracy is just a proxy metric. So good luck for those working with a notebook right now or during watching the recording, and let's get started. So I'm gonna restart my kernel just in case, and press run all. Actually, I should have done this probably from the very beginning. Now we probably gonna wait 1 minute or two while the data is loading. Yeah, so this second worksheet says please do not touch this worksheet, and that's what we're gonna do. We're gonna skip it. It contains just some inputs, etc. So right now, while we have some data loading stuff happening, we could skip it a lot and check the previous outputs from the previous run. So what this code cell does, it just loads the experimental data. It loads simulated data for the cascade experiment from the S3, applies some pre-processing and so-called quality cuts. So it keeps only those simulations of air shower for those the cascade experiment could produce reliable measurements as defined by the developers of the cascade itself themselves. So we have after pre-processing and everything, we have two arrays, matrices train and features train. They have slightly over 100K training samples, and for matrices we have a 16 by 16 by 2 array, and we have an array of 10 features for each detector shower. After the workshop, if you want to take a deeper look about the data, here's a link to the manual created by the Cascade engineers. They explain all the intricacies of the raw data there. But now let's move on. So what our code does, it actually removes. Actually, we had 3 16 by 16 arrays, not just values of each. So let's return back for a moment. So here we have an array, and we have 16 by 16 dots, and for each of these dots we had 3 numbers. So the first number is the amount of electrons captured The second one is amount of muons captured, and third one is the time when detector triggered since the start of the event, because like usually cosmic ray falls like not strictly vertically, but with some angle. Some detectors are triggering earlier than the others, and this information is also very important for us. But instead of accessing this information directly, we will be using another features that I will tell you in a moment. So we have 10 features. Since it's the simulated data, we know what was the original particle type, proton, neutron, silicon, ferrum, and so on. We know the energy of this primary particle. And we also knew its physical coordinate. Regarding to the center of the array, we know its XY coordinates and angle. And we have, like, as I've said, electron muon numbers. We have electron muon numbers for the whole array. So let's take a look. We could just take a quick glimpse at distributions just to take a look at what we have. So, for example, energy is shown as a log of 10. So 10 power 15 is like most of our samples are in range from 1 to 10 peta electron volts, and we have core distance. So zero means like in the very center, and coordinates like plus minus 100 meters. And we have the distance, angles, and so on. So let's take a look at the matrices. So here is the matrix for the electromagnetic detectors. Notice the hole in the center. This hole is where a colorimeter and some other auxiliary equipment for the array is located. So unfortunately, we don't have any measurements from this point, because in the center we have the computers that like collect all the informations from these detectors. And we have, unfortunately, even larger hole for muons, but as we'll find out, it's still enough to make reliable predictions. And here's how one air shower looks. So on the left, we have electromagnetic records, and on the right, we have muon detectors. And here we have some data pre-processing. If you're working with notebook directly, you could try to tweak something with it. But for now, we could move on. Also, if you're working with notebook, by default, we have some quite large feed-forward network used for training and making predictions. But if you want, you could start from simpler ones and try to build upon them and make something from scratch yourself. As you can see, the architecture is actually quite simple, just a feed-forward network with batch normalizations and dropout. We have nothing really specific here for the sake of the example, because the key stuff we'll be looking at is not the model itself, but how the model performs with regard to uncertainties we have in our data. So let's move on. Here we have also a pretty standard training loop for any PyTorch model, nothing specific, only maybe learning rate scheduler and early stop logic. And while I was talking, the model have trained. So here we can see that after some time it started overfitting, and we saved the best model, luckily. And here's the confusion matrix that we got with the default setup, roughly 50% accuracy, which is surprisingly good by astrophysical standards. So because like these energies are so high and we have so high uncertainty while dealing with it, some astrophysicists told me, well, if we guess the order of magnitude, then it's accurate enough. Because if it's Pevatron and not if it's like a matter of peta-electron volts and not tera-electron volts, then it's enough for us. So let's just open this confusion matrix in a separate tab just for the sake of the future. So here we could see that our model has found a shortcut since protons are very light and iron nuclei is very heavy. What the model does, it learns first of all how to distinguish very light particles from the very heavy, and it's performing good at identifying those two. But if you are looking in the middle, like at helium, at carbon or oxygen, the model performs worse there. Later on throughout the workshop, we will try to apply class weights and see whether it will change anything. But for now, let's keep in mind that our ultimate goal is not to simply classify the primary particles. Our goal is, given the flux of cosmic rays coming for us throughout all these years recorded by Cascade, our goal is to find out what was the mass composition of these particles. So we have energy, we have mass, and ideally we should build a chart that would be accurate enough so we could later on other astrophysicists could build upon it and check if their models and theories are checking against this data. So when we have finished training our model and got some the best accuracy we could achieve, we proceed to the next step. And what we do here is that we take all the predictions that we have made and then we take 5,400 different samples of them. And what's the reason of this? Because the data we are training on is simulated. It has the predefined number of each kind of particle. So we have some specific amount of protons, some specific amount of helium, some specific amount of carbon, etc., etc. And when the model trains, its learning objective is also dependent on the proportion of these particles, proportion of amount of each particle in the data set. And the problem with that is that we don't know how many particles of each kind we actually have out there in space. So our confusion matrix could look like good and be reliable enough on one hand. But for example, if we take into account that actually we have not a lot of ferrum, and actually we have a lot of protons in helium, and for helium we have a drop of performance, then our model performs not so good. And if we have not really, and actually we don't have a lot of ferrum, so we have a lot of lighter particles and heavier ones are rare. So when the model finds a shortcut like this, its performance grows up. But from the practical standpoint, from finding the mass composition, it's actually a bad thing. So what we do is that we take a few thousands of random samples of the test set with predictions, and then we analyze the stats from these subsets. So, for example, if you don't know for sure what are the proportion in the real data, let's try to take random proportions from the test set and try to check that there are at least no such scenarios when our model performs really bad. So this is what this chart shows. We have, let me zoom a bit. We have again our 5 classes. from hydrogen to ferrum. So the nuclei of hydrogen is proton, so these two terms are interchangeable. So what does it show? It shows the average error our model makes for each particular class, for each for all these 5,000 random sum samples of the test set. For example, we saw that our model performs like really well, 67% accuracy on protons, and we will take a closer look at helium. We could see that yeah, most of these random subsamples, they have really low error, and if you will take the tail of our distribution also, it ends at somewhere about 30%, which is quite good. But if you'll take those models that we have in the middle, like helium, carbon, silicon, etc., you will see that they have slightly higher error. So we could see like the mean one is 12% versus 8%. But if you'll take a look at the outliers, you'll see that some of them are showing 60% error. This tells us that there are that there are some possible scenarios, some possible compositions of these rays, for which our model is not ready at all, and that's a bad thing. And when we are working with like our data, we need to take this into account. So what we do? So let's take a look at the second. Oops. So let's take a look at the second picture we have here, and this is basically the same chart as the previous one, except that the previous one was showing absolute errors, and this one is showing like real values. And here we also have very specific metric, a very important metric is the difference between the true fraction of particle of each kind of in the data set, and the delta between the true proportion and predicted one. And we could see that in this particular case, our model it shows 2% higher fraction for hydrogen and ferrum, because like it's easy to distinguish these two, ultra light and ultra heavy. So the model tends to assigning all the particles in the middle to either one of these two classes. And as a result, we have smaller than real fractions of silicon, carbon, and oxygen. But also, it's a very interesting thing that for helium, we have a very low error. So it's just 0.5%. And it's really interesting, because if we will would take a look at the confusion matrix, we would see that numbers are not really different. So we have 39% accuracy and 37% accuracy for helium and silicon correspondingly. But if we would take a look at these fractions, we would see 0.5% error versus over 2% error. And this is why accuracy could be sometimes not important for us, because, for example, if we had the similar, if we have this same kind of error between two adjacent classes, so for example, if 5% of carbon is mixed with 5% of helium, so we predict 5% of as first one, as the 5% of second one, and etc., that in the end we will get the same mass composition. So while we get a drop in accuracy, our downstream metric, like the accuracy of the mass composition, it remains the same. And that's why we should somehow, sometimes sacrifice the accuracy of our model, use some heavier regularization, or introduce class weights to get lower accuracy figure, but in the end, but in the same time, we'll get a more robust model. And before we proceed to tweaking our model and trying to make it more robust, there's also a few little things that are out of scope, like of the coding exercise for this particular laptop, because it would take a lot of time, and we don't have, unfortunately, the opportunity to do this in action. But still, I would like to just show you some figures of other challenges that we meet while working with these discrepancies between experimental data and simulations that we use for training. And one of them is that since Cascada was an array staying like in open air 24/7 for over 20 years, from time to time it simply breaks apart, and some of the stuff just stops working throughout the experiment. So we have 300 million records, and for some percent of these records, we have cases when some parts of the detector simply stopped working. And actually, well, I have a spoiler in the title. We found out, like, when we found out, we were quite scared, because like we were not sure that because like at some point we have already released a paper with some analysis, and we haven't spotted the erroneous records yet. But as it turned out, if you use dropout throughout the training, it not only works as a regularizer, it also makes model robust to such kind of anomalies. So while on some charts they could look really scary when just a part of your data disappears, turns out that the model is quite robust and could handle it pretty much. Another thing that is very important is how the accuracy depends on the energy. And also the question is, or the answer is simple. The higher the energy, the easier to classify the event. And I think it's kind of logical, because the higher the energy, the more particles you get in the end. And the more particles means more information, less uncertainty. So it's easier to get more robust results. But as we saw also on this chart with energies, most of the events are happening to be in about peta-electron volt to 10 peta-electron volts range. So it's a good thing that our model is robust when it comes to analyzing ultra high energy particles, but it's a problem that such particles are extremely rare in the nature. And almost finally, I wanted to say finally, but it's not. We are not there yet. Is the spectra of the simulated event. So because we are working with the simulation, all the numbers there, they're like forming the straight line, and on the left we have like the real distribution, and on the right we have what our model has predicted. So the color means the type of the particle, and the x-axis means energy from 1 peta-electron volt to slightly over 100, and the y-axis is the number of the events that we have in our test set for a given energy bucket. And now I'm gonna demonstrate a graph that we have obtained from the experimental data. So because we have 300 million events, we are not gonna analyze them throughout the workshop, but I'm gonna nevertheless show you just how the results look like. So just a quick reminder. So here's the simulated data, and here's how the spectra looks like for for the real data. And the most interesting thing from the like cosmology perspective, from the astrophysics perspective, is this kind of break when lighter cosmic rays decrease, such as hydrogen and helium, and in the same time heavier ones increase. This particular anomaly, no, this particular case is called CNI, and the interesting thing is that so far we don't know why it looks like that. So we don't have a reliable theory while at some over some energy we have over some range of energies we we have we detect heavy particles more often than lighter ones, and that's why important. That's why our work is important, because like by obtaining more and more accurate data, we could try to at least narrow the spectrum of possible astrophysical models that could explain how these kinds of particles are being produced, what makes them, and why we see heavy ones but don't see lighter ones, while for the lower energy ranges it's exactly the opposite. So there are some speculations that, for example, some light high energy particles simply do not survive the travel to Earth due to some different reasons, but I will leave this stuff to like real cosmologists and won't try to discuss it. And finally, from like the theory and the evaluation perspective, there is one more thing that we could do. So we have the predictions of each of the amount of each particle for each like energy bucket, and we have plotted them and so on. But we remember just that just a few cells ago we have tried to estimate the accuracy of our mass compositions for each particles, for each energies, and we just found out that for some particles we have lower percent than it is in the real world, and for other particles, well, for some it's higher, for some it's lower. How could we use this info? So, for example, if we know that these predictions are not entirely correct, and we know that there are some metrics that are more or less reliable, that say that we probably actually have more hydrogen that we have, and we probably have less silicon that we have. What could we do? So there happens an unfolding process which is being done by scientists from another university that we are partnering with. I'm not working on this particular math stuff, and I could only give you a rough understanding. So what they do is that they break the confusion matrix into energy buckets, as it being shown here. Then they compute inverse matrices for each of these energy beams, and then they apply these inverted matrices to this chart. And by doing this, on one hand, they introduce uncertainty, and we could see that error ticks are much higher on this chart than on this one. But in the same time, they also try to account into uncertainties between the simulated data and the real data. Because the key problem with training on the simulated data is because it's being based, it's based on the most advanced physical theories that we currently have. But in the same time, we know that they are not accurate enough. So this is currently the best that we could do to try to keep these uncertainties, take them into account. And we have finished with this stuff, and now what we could do we could do some simple thing. So we have a baseline model. If you have opened the workbook, you could try to play around with it on your own. What I'm gonna do, I just saved these two particular charts, so like confusion matrix and the chart showing differences in fractions. And I'm gonna try to do a simple thing. I'm gonna retrain the same network, but this time I will add some class weights, and let's say 1.15 here, 1.25 here, and see how would it affect both accuracy and the mass composition estimates. Yeah. In the meantime, it should take a few minutes. Are there people who opened the workbook? I see that a lot of people are watching me. I could watch you too, by the way. Yeah, so just a quick reminder, if you have missed it in the very beginning, once you have opened my notebook, you will see a notification bar at the very top saying that it's available only as a read-only for you. But if you press File and then Clone, you will get a copy in the cloud just for you. And the neat thing is that it will also copy all the data sets, all the data we are working with today. So you could try and then just press Run and choose Run All to kickstart it. And let's see, it's still training. It seems to converge. Okay, so our previous best model converged at 50%, and now we have a slight drop. And for the sake of the simplicity of this particular notebook, we haven't implemented any like specific comparison stuff. So we could simply try to switch between these models and see that our new confusion matrix has much higher accuracy for the carbon and oxygen. So we had like 34% before and 44% now, because like overall accuracy seems like hasn't really changed. It all happened at expense of the other kinds of particles, like being less accurate from now on. But maybe it will also, yeah. Okay, so we're still computing all these subsamples of the test set, and when they will be computed, we will be able to compare these kinds of graphs. Let me copy this one as well before it disappeared. So because 60% is a really high level of uncertainty. So on one hand, it's really unlikely that this tail end scenario could happen. We still should take it into account, and at least we should treat it as an indicator of the model being unstable under some specific scenarios. And we have 3,000 samples out of 5,400. So it should take about a minute and a half. And at the same time, are there any like intermediate questions? So maybe I should repeat something or elaborate. Or so far so good. Okay. While it's happening, we could actually return to the data loading worksheet, because I have kind of skipped it and try to take a closer look. So here's the stuff that I was talking just before. So in this simulated data set, we have some predefined amounts of part of the particles of each kind. So the one stands for hydrogen, the two for helium, etc., etc. And we have some random well, not random, the logarithmic, but still numbers. So we have like 30K for hydrogen and so on. And we don't know for sure what are the real numbers. And energy, disregard the lower cut at the 15. Energy seems to be more or less comparable with what we have in the real world, which is on one way, on one hand, it's a good thing that we have like the same energy distribution, just like we have in the real world. On the second hand, it's actually a bad thing, and it's not in my power to change that. It was a decision made by the developers of the Cascade array themselves. But having so little training samples at the end of the distribution could mean that our models could perform bad while working on these ranges. And yeah, so the coordinates have normal distribution, which is quite expected. For azimuth, we have like a range from 0 to 359 degrees, which is also expected. And I think by this moment, yeah, so it's ready. And let's see. So the maximum value of our like mass composition errors hasn't really changed. It's still the matter. It's still at about 60%. But you could try to take a look at the relative error and see that actually. Let me close like this one. We don't use them anymore. And we could see that actually, let me zoom, they have become worse. Let me zoom in. 177. Yeah. So like before that, we had an error at about 2%, and now we have an error at about 3 to even 4%. That's why actually when we are training this stuff for research purposes, we simply run hyperparameter search and then try to pick models not with the best accuracy, but like with the best systematics measurements. What we could do as well is we could try to, aside from playing with the class weights, for example, we could try to use more aggressive dropout and see whether it will affect our metrics somehow. So the stuff that would be really neat to achieve at the moment is to see a scenario when the accuracy of the model drops a little bit by, say, like from 50% to 49, 48. And at the same time, we'll see some possible increase in the systematic measurements of the model. So like on one hand, it could become less accurate, but in the same time, it also could be more robust. So it would be robust in its erroneousness. And we could use the same scenario again. So we could try to see whether it converges. Still about 50%. Okay. We could take a further look at the data distributions that we have here. So one of the piece of, like, for those watching the live stream and well, for those people who are working with a notebook, I just realized that one of the tips that I haven't included in the to-do comments is the fact that you could do some very basic feature engineering with the azimuth angle. So for example, as we all know, like 360 degrees and 0 degrees means the same stuff. But for the model, these are completely opposite features. So ideally, the model should learn that fact that very high values of this particular features should mean the same as the very low values. But you could try to do some feature engineering, for example, compute this sine and cosine of this angle and see whether it would affect the result. So the total number of electrons and muons doesn't seem to be really interesting feature as for us, because we already have all the measurements from each of the detectors. But still, let's use them. Why not? And also another thing that I haven't included, that I haven't described yet, is the shower sage. This is a parameter describing the shape of the air shower, because like the cosmic ray is being usually caused like only by a single particle. A single particle could be small enough that it flies through the atmosphere without hitting anything immediately. So like depending on how high or high low the first smash occurred, the cosmic ray will produce the different shape later on. So it depends on both, like simply the y-axis differences, but also like on the fact that lower layers of atmosphere, they have higher density, and so on. And we have about 2 minutes left for computing the random sum samples of the model, and I have both charts here from the previous runs, and we'll try to compare whether our quick tweaks were anyhow helpful for getting these for getting better systematic results. We'll see. Is there like any more questions? In the meantime, I could also share just a couple of details of the JSON project that is out of scope, like on this particular notebook, but is directly tightly intertwined with this particular research. Aside from analyzing mass composition of cosmic rays, there's one very specific thing that we also do with this data, and it's namely searching for photons for gamma rays. So gamma rays also could be primary cosmic rays, and the reason why they are emitted from this data set, while the lightest thing we have here is the hydrogen, is the fact that photons are extremely rare compared to any other kinds of cosmic rays. So usually they are 1 million times they occur in 1 million times less than the other kinds of cosmic rays, and it makes them incredibly hard to find. But aside from all the other kinds of cosmic rays, there's one very important thing. It's the fact that photons don't have mass, and that means that all the other kinds of cosmic rays, while they are flying from their origin, be it a galaxy center or anything else, they will change their trajectory at some unpredictable angle. So when we are finally detecting them, we don't know where they are originated. In the same time, photons have direct trajectory. The only thing that could move them are black holes. So, for example, when you detect a photon, if it came from this direction, you could be absolutely sure that the source of this proton, it was right there and not somewhere else. And for example, when we find ultra-high energy photons, this information is also extremely valuable even if you find just one or two of them from these hundreds of millions of events, because they point us directly at the point where like other telescopes and observatories could try to monitor, to find what creates such kinds of ultra high energy particles, because so far we don't really know. And let's see at our chart. And here we have some slightly stable results for hydrogen and ferrum in our first run, but it also happened, unfortunately, at the expense of helium and carbon. So we try to find some middle ground between them. So now it's equally bad and not like some really good and really bad particles, which is also like an achievement for such kind of workshop. And I think that's it. And we could like finish the workshop part. So thank you, everyone. Feel free to ask questions or follow-ups in the comments. And if someone would make a better model with higher than like 50% accuracy, just let me know and we will include you in our next paper.
Thank you, Vladimir. Any questions? But I guess it would be pretty difficult to ask questions about that. I can imagine.
Yeah, I'm sorry for that. I've tried to make it like as easy to start with.
But I mean, like in this room, we have like really hardcore people though, that can later like brag to all the other ones up there that they managed to witness it. So thank you again.
Thank you.